Hello, hi, I'm Jeff, a PhD student from NYU. I'm here to present how to train a robot to do tasks from uncurated data. So robotics has been solving increasingly complex tasks with imitation learning, like dexterous manipulation on the left and pick and place on the right. And the current modus operandi in robot learning is learning from task-specific data. So if we want to train a robot hand to rotate a bottle, we collect imitation data from this. And if we want to do pick and place, we also have to collect a specific set of demonstrations. So obviously this is expensive. Task-specific data set curation is bad for scaling. And this is in stark contrast to the latest models in vision and language, as we all know, like diffusion, where you give it a text prompt and you give it a nice picture. And this task-specific behavior is prompted from large models trained on diverse, task-agnostic, internet-scale data. Like language models have been doing prompting and generation for many years now. For example, here I can search for safari and hiking options around Kigali, and it generates a decent response. And also, we train them on internet-scale large data sets and use prompts for downstream task specification. So the natural question is, can we do the same for robotics? How do we train a single robot policy from diverse, playful, task-agnostic data, and then we do multiple downstream tasks with no extra labeling? Like, this is doable. To illustrate the point, consider this toy example. Suppose we have this red car at the bottom, like mid, and we want to learn to go to point 1 from here up top. So we collect a set of demonstration trajectories that go through point 1 and imitate it with behavioral cloning. This is a specific task, specific data set. Classical behavioral cloning works very well here. But classical behavioral cloning has a bunch of assumptions. So let's quickly go through the recipe. First, you get some demonstration trajectories. We assume that these are expert trajectories completing specific tasks. And then given each frame, we regress on a ground truth action. You assume that there's one correct thing to do at one time. So this generally assumes a unimodal Gaussian assumption. And do this for each frame in the data set. Assume a Markov decision process, right? Now, suppose instead of this clean, specific data, someone just gave me some uncurated mix of demonstrations of driving around these two blocks. As a minimal example, it could look something like this. There are no task labels anymore, just trajectories. But we still want to train a single model on this uncurated data and be able to go to all of the places covered by the demonstrations. For example, both point 1 and point 2. So how do we specify tasks in this case? And what if I want to go to point 3 here in the middle? There are two demonstrated ways to go there. So how do we model this? At the very start, we can either turn left or right. So the action distribution here has multiple modes. If we just regress on a ground truth action, our model will either collapse on one of the modes and always choose one route, or worse, we just fit to the mean and go out of distribution straight up. So it's not unimodal anymore. And if we start turning right and then change our mind halfway, we end up driving down the middle. And so we need to be able to pick one way, remember what we did just now, and follow through with the decision. So otherwise, we'll go out of distribution and crash and burn. This means that our action has history context and it's not Markovian. So as you can see, large-scale task-agnostic demonstrations violate these classical behavioral cloning assumptions, as we see in this toy example. So how do we extract useful behaviors from uncurated demonstrations without adding human labels? So to specify tasks on this uncurated demonstration, we condition with future observations. The key idea is that every future observation in the trajectory can be seen as a goal state. So suppose the car is now at the bottom here again. Given the current observation, we can sample some future observation along the demonstration trajectory, assume that following the demonstrated sequence of actions takes us from the current to the future, which is a pretty mild assumption. During training, we would randomly sample current and future observations along the demonstrated trajectories. And during rollout, we prompt the model with a target future observation. And this is like when you go get a haircut and you prompt your barber with a photo of your target hairstyle. And then the barber closed loop generates a sequence of toolpaths that transforms your hair to your target hairstyle, right? And we can explicitly model the action distributions with multiple modes. Suppose on the right we have an action space, and each point is a demonstrated action at some state. We can discretize the action space with k-means and represent each action as the k-mean spin center plus an adjustment residual. So we train the model to predict both the category and the residual. The categorical covers the multiple modes, and the residual will cover the whole continuous action space. To model context, we just use a sequence model, good old transformer encoder, and now we have this formulation. Given a sequence of current and future observations, we predict a sequence of actions where each action is in the category and residual form earlier. And we call this method Conditional Behavior Transformer, or CBET for short. And so we ran this model on some simulated environments. First, we tested it on this toy example earlier in the Carla driving sim environment. Our method, as you can see, comfortably models both routes and drives around the left block or the right block, depending on the target observation image that we feed it. And here's the block pushing environment, where the goal is to push the blocks into either same or opposite colored goals. Again, we can condition the model with a given future state where the blocks are already inside the goals, and the model will push the blocks accordingly. And here's a simulated kitchen where a Franco robot interacts with the kitchen appliances. So we prompt the model on a final target state, and the model will do the task conditionally. So we compared it with some baselines. We ran a few imitation learning methods, some offline reinforcement learning methods with proxy rewards, and some ablations. And as you can see here and from the rollouts just now, our method performs very well on a sim benchmarks and is able to capture task-specific behavior from these data sets. So can we do this on real robots? And it turns out, yes. We can learn a task-centric real robot policy directly from uncurated task-agnostic play data with only vision and robot proprioception. So last summer, we set up this toy kitchen and a Franco robot arm and collected 4.5 hours of playful interactions with it. And as you can see in this video, this is a long sequence of uncurated actions with no resets in the environment. And it still exhibits expertise on affordances and motion planning, and so we can imitate that and generate desired behaviors at runtime. So the problems are the same. Play data show expert behaviors, but otherwise has no rewards or labels. It is unstructured. Its action distribution is multimodal in the sense of multiple modes. There are multiple ways to do multiple tasks. So here, there's 2 ways to close the oven door, right? It's contextual, just like the toy example earlier. So for example, here, are we putting the pot down or picking it up? Given a context, it becomes pretty obvious, right? It's moving in opposite directions. And so to train with the robot data, we pre-train a visual encoder with self-supervised learning. Then, from the unstructured play data, we sample a slice of current observations and some goal observations up to some horizon in the future as the prompt. And we train the transformer encoder to predict a sequence of actions in a category and residual form as shown earlier. Now, we can generate task-specific behaviors during rollout with the future observation as the prompt. So on the left, here's the prompt. If we prompt it with an open oven door, the robot will just happily open the oven door for you. And starting from the same position with the same model, if we prompt it with the pot already in the sink, the robot will put the pot in the sink. And if we prompt it with both the microwave and the oven door open, the robot will open both. And we also see spontaneous retry behavior here. So you can see that the robot gripper didn't catch the oven handle on the first try, but went back and to retry a few more times. And since we modeled multiple modes, this model can also choose to open the oven door first and then the microwave, given the same prompt condition on the same model. So we also tested the robustness of our model by perturbing the scene with unseen objects. As you can see, we've added a bunch of flowers and decorations to it. We see that the model stays robust up to some level of perturbation as we use self-supervised learning for the visual representations. And of course, it fails when we add a lot of unseen objects to the scene. It goes out of distribution very fast. So what's next? It could be more robust against perturbations, as you saw earlier. And furthermore, even though our data is uncurated, our robot environment is highly controlled, as you can see, with backdrop curtains and stationary camera mounts and everything. And our model works on this particular toy kitchen setup. So it would be great to make this work across multiple toy kitchens or even more complex real-world environments. To conclude, this is our work on conditional behavior transformers. The takeaways are, we can train a task-centric robot policy with uncurated task-agnostic play data. It works with images, trains completely offline, and does not need rewards or labels. If you're interested to learn more, you can take a look at the website here, and welcome to drop by our poster later at number 22. Thank you so much.
Great, thank you. So we have time for a short question. Are there any questions in the audience? Yeah, just one up here.
So to this work, would you like to add something like beam search, where for the car you maintain different beams, and maybe it will help in more complex situations, like maybe you go on the right path, but it is taking a longer turn, and on the left part it is a shorter turn, things like that, and you can measure the distance from the target point as which way to choose. So suppose you can take a turn which may seem to be closer to the target, but it takes a longer route, then you may choose the opposite path, something like that.
Yeah, I think that's a great question. Yeah, so beam search and other planning methods, we haven't tried it out. But if you see the recent advances in robot imitation learning, you'll see that you get to this point where you don't predict like one action in the frame. You predict like a sequence of like 50 or 80 or something actions into the future. So you model a joint distribution of a bunch of actions, and this is kind of the same idea of like you model a whole trajectory. And I think that yeah, it's a great idea. I think we could probably try that out as well. Yeah.
Great, thank you for the question. And let's thank the speaker again.